Right, hi everyone. Welcome back from spring break. For those that are here, some of you might not have gotten the memo, but spring break is over. Classes are back in session. So we got just a couple more weeks left for the semester. So I put up an announcement this morning just about the general plan, about what is due when. So this week, well, we have got one more reading quiz due before Wednesday's class, and I won't have any due during the last week of classes. And homework is due today. You've got one more homework assignment that will be due next week on the material that we covered this week. And then we've got our exam on May 10th. So that's Monday at this time. It's scheduled from 11 to 2, but it is not a final. It's kind of like a midterm, so it should be as long as the other exams. And so in addition to that, I also posted a link to the FCQs. So please do go on and complete your FCQs for this class, for all of your classes. That's really, really helpful. And actually, we use that feedback as part of our evaluation process in the department. So your feedback is definitely appreciated. And as I said, if I get up to 80% of the class responding, that means the department will be happy. So that I'll be happy. And that's really useful for me. And I'll give you guys 2 extra bonus points as long as the response rate is good enough on the evaluations. Okay, so before we get started, we're going to work on worksheet 21 today, which is dealing with composition and inverse functions. Any questions about the plan for the rest of the semester, or anything else? Almost there. I know it's been a difficult year in many regards, difficult time being a student. So I definitely commend you all. I think you guys are doing a great job, and we're just about at the finish line. Okay, so for today, yeah, we're going to talk about 2 ideas and wrap up kind of the material in chapter 12. And then starting on Monday, we'll start to talk about ideas about cardinality of sets and countable sets, uncountable things, and things like that. Yeah, so these ideas, composition, invertibility, I'm certain that you have seen in other prior math classes with functions that go from R to R typically. So I want to kind of take a look at these ideas first, using kind of more familiar examples, and then working to things like power sets and other things that you probably don't see in calculus. So when we talk about composition of functions, that just means if we're composing G with F, that means we kind of start first by taking the input, plugging it into F. We get a corresponding output from F, and then we take that output of F and use it as the input into G, and then get a final output. So when we compose things, we need to be careful that things match up. So if I'm composing F and G, this works because what I get out of F is exactly the same. The codomain of F is equal to the domain of G, and that's what we need. If I wanted to use these functions over here and consider how would the map F of G of B work, this would be undefined, right? Since we would first plug it into G, we get something that's in set C, and then we would want to input this into F, but that might not be in here, right? So we have an issue if we were to try and compose things this way. So the order that we compose things certainly matters. It might be defined one way and not the other way. Any questions about this idea of composite functions? Okay, so the first couple of ones are kind of examples from that you probably have seen in calculus, and then C is probably something that you haven't seen in pre-calculus or calculus class. So let's just kind of think about A together and then give you guys a chance to think about B on your own. So the questions here are, let's think about how we can compose these functions, G with F and F with G. And then after we compose them, if it's possible, let's think about whether the resulting map, the resulting function is injective, surjective, or both of those things and bijective. So if I were to compose this, say going, we'll do G of F first. Right, we start off with this function first. So it kind of goes from R to R. And then we move over into this function second, which goes from R to R, right? So this kind of works out here. This is not typically how we write the domain and codomain of functions. We would typically, right, ignore the intermediate thing, and we just think about it as something goes into this function, and then it goes into F, and then it goes into G, and then we get one output of this function. So this would be a map from R to R, is more normally how we would write that. And in this case, we would say X first goes into F. So if I want to do some scratch work here, one way that we could write this out, right? Oftentimes we see composition written like this, where I'm plugging F of X inside of G. And so I start by saying, well, what is F of X? F of X is X squared, and now I plug X squared. Right, in place of the X that was in this second function. So, you know, there are different ways that people write out functions. Sometimes they might write it out like this. And sometimes we use kind of this notation to kind of indicate X is mapping to sine of X squared. So you're happy to use whatever representation you want. So the domain and codomains of F and G, they all match up. So this is defined. We've got a formula for it. And the next thing to think about is this injective and is this surjective? So what do you guys think about injective? So we'd like to think about if two inputs are not equal to each other, then their outputs should not be equal to each other, right? Or in other words, right, each input should, we shouldn't have two inputs that are mapping to the two different inputs mapping to the same output. Anybody have any thoughts? Let's see, I got a chat. Okay, so people are saying not injective in the chat, at least to me. That's right. When you see things like X squared, that's usually a good warning sign about something not being injective, because positive and negative things would go to the same point. So if we have X equals 1 and X equals -1, they both sorry, here I was doing G composed with F. So this gives us not injective for that one, because we have two inputs not equal to each other that go to the same output. And here we want to be careful that our domain is R, right? We could think about restricting this domain so that it would be one-to-one, but over its entirety, this is not going to be one-to-one. Any questions? Okay, and then for surjective, what would you guys think about that? Okay, remember surjective means we map onto the codomain. So here the codomain is real numbers. So what we're thinking about is it possible that this function has a range of all of the real numbers? So I am going to open up a poll here since I'm just curious what you guys are thinking. Let me edit this since, well, okay, I don't feel like editing it right now. It says one-to-one on here and injective. What I'm asking about is surjective. We did the injective part. So the question is, do you think this function sine x squared is surjective or not? Okay, if you haven't voted, got one more person, please take another 5 seconds or so. Awesome. Thank you. Okay, so here were the results. We had pretty split. So we had 4 people say no. Well, 5 people say no. Sorry, I should include the definitely. 2 people that said yes and an undecided. So this one is not surjective. And when you're working with sine and cosine, usually that's the case, right? Because what goes in, typically you think about this as an angle. What comes out of the sine is the y coordinate at that angle on the unit circle. And since we've got a unit circle, right, where you have a restriction in the range of values. So this is not surjective. So for example, there was no x value. Such that sine of x squared is equal to 2, for example. And 2 is in the codomain of this function. Any questions? Okay, so maybe what I'll do is break us up into 2 groups, put Lindsay with one group, and I'll kind of stick with the other group. And we've done one of these directions for this one. Think about doing the opposite direction in terms of composition. So think about what would it look like if we compose F with G and go through the same exercise here? Does the map work? What would the formula be? Using that formula, do you think it's injective, surjective? And then we'll see how long that takes. We can move on into part B and do a similar analysis over here in part B. Any questions? Okay, so I took notes down from the group that I was working with, but I guess generally speaking, for the other room, were you guys able to work through part B? Yep. Okay. And so I'll compare, I'll show our answers and just let me know if you disagreed with anything. But for f of g, I did that in green on the right up here, we got sine of x squared. This was neither injective nor surjective for similar reasons that the other one didn't work. And then in part B, any questions about that from the other group? Then in part B, we if we do g of f in blue on the left, that was e to the x cubed. That was injective. And just recall that if you want, we didn't prove this, but wouldn't be a bad exercise to go ahead and prove it. And if you did want to prove it, a common way of proving injectiveness is using the contrapositive technique, which is, let's assume we have x and y in R so that the outputs are the same. Then if we can show that it follows that x, the inputs have to be the same, that proves surjective. So you could start with this equation over here and then just do algebra. Take natural log, take cube root, that shows this. And for surjective, no, the exponential functions have issues with being surjective. They only map to non-negative things. No, sorry, they only map to positive things. They don't even map to zero either. Yeah. So for that reason, that throws off the surjectiveness of both of these functions. E only outputs the positive numbers. But when we compose the other way, we can simplify it to e to the 3x. That's injective. And certainly people were making use of graphs, and that's totally fine, right? We've got the graph of e to the 3x looks like that. It's 1-to-1, but not onto. So some things that you might be thinking about are, in this case, this was injective and this was injective. When we compose two injective functions, we get something injective in this case. Is that always true? Similarly, this function is surjective. This function is not surjective. So what happens when we have something in our composition which is not surjective? Does that mean that the composition can't be surjective, or is it possible that it is surjective? So these are good general questions that I'll have you think about on the homework assignment. Here's F, here's G. This is injective, it's not surjective. What can you tell me about the composition of these functions? Any other questions that came up while you were talking about these? Okay, so good. So now let's move on and think about C, which is a power set function here. So now we have a set X, and we're mapping from the power set of X. F is the map, which is mapping from the power set of X to the power set of X by taking some subset of this set X. So taking some element of the power set of X, its map would be the output is some set, which is the intersection of A with this set Y, even numbers. So basically, notice these are the even numbers from the first positive 100 even numbers. So basically what this is saying is it's giving us the even integers in set A. That's the effect of intersecting them with Y. And then we're going to compose this with a second map, possibly. We have a second map G, which goes from power set of X into the integers by taking that notation, absolute value, when we apply it to a set means cardinality. So this means, and this is what our next topic is going to be. Okay, which is the number of elements. So first thing to think about is, you know, what would do these maps make sense, first of all? So if I go G, then F, right? That means I have to start with F. So I would start with the domain of F. And it kind of maps intermediately to the power set of X. And then G would then take that, I have a slight delay here. Right, so F is going from the power set of X to the power set of X, and then G would pick up from that and then map that power set. It would take the cardinality of it, and that maps it ultimately into Z. Right, so we can think about this as mapping from A to the cardinality of A intersect Y. And just keep in mind that this is telling us the number of even elements in set A. That's equivalent to doing that, right? And if we were going in the other direction and say mapping from F into G, or excuse me, first composing F with G, meaning so we first plug into G. So that means we start over here at the power set of X. Right, that maps us to Z, and then we would try and compose that with F. But we have a problem here in that the codomain of the first function doesn't match the domain of the second function, so this doesn't make sense. So we can compose it in one direction, but not in the other. Does that make sense? I don't know how good my microphone is. Can you guys pick up when people walk by? They're chatting. Sorry, mailman's here. It's my dog's highlight of her day right there. It's all downhill after that. Okay, so good. So we don't need to worry about f of g. That is not a defined function. So we'll just think about this function and what properties it may or may not satisfy. So injective, right? And so here again, we're mapping to the natural numbers, or to the integers, I should say. We could have said the natural numbers. Okay, maybe that'll give away one of them. But to kind of see how this is working, what we would, if we take an example, let me just take like A is equal to the set 1, 2, 3, 4. If I take G of F of A, you want to think about it in steps, right? The first thing it's going to do is intersect that set with Y, and that's going to intersect with elements 2 and 4. And then we apply map G to the set 2, 4, which would give us an output of 2. So plugging the map 1, 2, 3, the set 1, 2, 3, 4, which is an element of the power set of X, into this map, the output would say there are 2 even numbers in that set. So what do you guys think about, let me open up the poll again. And I think I have one that we can consider this. So now let's think about both of these. We don't need, not looking for like proofs, but if you're thinking about this map, do you think that it would be injective, surjective? Okay, got two more people that are thinking about it. Please take another 10 seconds and give it your best guess. Okay, here were the results. So 5 out of, I think, 7 people that got the response in said neither. We had 1 for bijective and 1 that said just injective. So the 5 that said neither are correct. This isn't injective or surjective. And so here's I did an example for set A above. So if I can come up with a different set B that has the same output, then that disproves the injectiveness. So let's kind of say, okay, well, we've got set A, which is 1, 2, 3, 4. And can you guys think of another set B, which would have the same output as set A? Yeah, okay, someone chatted in, 2, 4, right? Any set that has 2 even numbers would work. They don't even have to be the same 2 even numbers, right? So we could do like 10 and 12. They both have 2 even numbers. And as far as the surjectiveness of this set goes, because we're thinking about the codomain is Z, we think about the range would be, well, what are the possible values that we can get for the number of even numbers in this set over here? The range is quite limited, right? We're actually, right, at most we've got 50 even numbers in that set. So the range here are just the numbers from 1 up to 50. And since these are not equal to each other, this means it is not surjective. Any questions? All right, great. So in D, I just kind of started this. I think we talked about this a little bit. This is pretty similar to one of the homework questions that you have that was due for today, actually, where you had a rational function that you wanted to prove whether it was bijective. And so here's a similar idea here. And these can be tricky. And so I just want to kind of reiterate kind of the hint here. If you got stuck on this homework problem, is to kind of take this and write it as, you know, some write it in its remainder form type of thing, rather than leave it as x over x minus 1. So the way that we can do that is we divide x minus 1 into x, doing this polynomial division. Say, okay, the leading term of the divisor is, 1 times the quotient. That cancels out the x, and what's left over is a positive 1. So this tells me that x over x minus 1 can be written as 1, that's this one over here, plus the remainder, which is also happens to be 1 here, over x minus 1. So in other words, we're kind of just decomposing that fraction into, if we added these back together, you can always check that we do get back x over x minus 1. So my suggestion would be to maybe think about this function f of x is equal to 1 plus 1 over x minus 1. And it's going to be easier to use this function to prove injectiveness, for example. So to do that, you could do a contrapositive technique here. And now you can see that we're kind of set up for a little bit easier algebra to show that x is equal to y. You can subtract 1 from both sides, flip the reciprocal of both sides, and so on. So at this point, it's algebra. To prove that something is surjective, then we would need to show that everything in the codomain is in the range. In this case, the codomain is the real numbers excluding 1. So one way to prove surjective is to pick an arbitrary element in the codomain, excuse me. And then just show for given any value of c, here's how I could find a value of x that's going to map to c. So this also becomes an algebra problem where you can think about taking this equation and solving for x. And if you can show that we can solve for x as long as c is not equal to 1, then we'll be fine. Any questions? Okay, so next up are these questions here that deal with equivalence classes a little bit. This is also something that's on your homework assignment, so this might be a good opportunity to see if you had any trouble with that so far. But in E, we're thinking about R being the equivalence classes relation mod 3. And C is denoting the equivalence classes on Z. Okay, and so we've got 3 of them that we can write out. So this would be all of the things, the equivalence class for 0, right, just recall would be right, all of the integers that are divisible by 3. Equivalence class 1 would be all of the things that have a remainder of 1 when we divide by 3. And so on. So those will be the equivalence classes mod 3 in this case. We have 3 of them. These partition all of the integers, etc. So the map that we're defining here, we have a composition of 2 maps. F is going from z to z, just multiplying the integer by 3, which is giving me another integer. So just one thing to note here, this map F is 1-to-1 and onto. So F is actually a bijective map. And then we're going to take G and is going to map an integer to its equivalence class. So for example, the number 4 would get mapped to the equivalence class of 1. So if I take f of g, right, that means we start with g, and we would go from z into the equivalence classes of c, and then f would want to pick up and take an integer and map it to an integer. But this does not make sense when we plug that into f, right? Since the codomain of G does not match the domain of F, that means we can't compose in this order. However, when we first do F and then do G, things work out. So this would take an integer and ultimately map it to an equivalence class. So here what we're doing is we're taking X, mapping it to 3X, and then taking the equivalence class of that resulting integer. Any questions? So maybe we'll start with injective and then surjective. So the question again is, okay, we've got this map. One of them is defined, one of them isn't. For the one that's defined, G of F, let's think about whether this is injective or surjective. So if we're thinking about the surjectiveness, we can think about the codomain and then compare it to the range. So the codomain would be the equivalence class mod 3. What would the range of this function be? So when we're thinking about the range, right, in the end, we're getting equivalence classes. So we get an integer, and then we think about what is the equivalence class mod 3 of that integer. So if you think about like what would happen if I took G of F of the integer 7. right? So f says, let's take that integer and multiply it by 3. And then g says, let's take the equivalence class of that integer. And the equivalence class for 21, if I'm using these representatives, 0, 1, and 2, which one does it match up with? So which equivalence class does 21 sit in? Yeah, sits in 0. And if you think about this, right, there was really nothing special about 7, right? If I pick any integer here, once I multiply it by 3, the thing that I get is going to sit in the equivalence class of 0, right? Because it's divisible by 3. If I put a 2 here, total different story, but there is something special about this being 3 and that we're taking a look at this mod 3. So these relationships might be surjective and injective depending on the map. So in this case, the range here, everything just maps to this. So no, since the range and the codomain are not equal to each other. And I think that probably answers the injectiveness as well, since the range has one thing, right? We're mapping every single integer gets mapped here. That's pretty much like the opposite of being injective. Okay, any questions about that? So maybe I will skip over F for now. That could be something good to practice since it's pretty similar to E, except now we've got a different map. Instead of multiplying by 3, we're adding 1 and then taking the equivalence class mod 3. Okay, so with this notion of composition, we need to define what it means to compose functions in order to define the inverse. And functions having inverses are really nice, right? Sometimes it's nice to know if I have a certain output, can I figure out what was the input that led to this output? So you can think about plenty of situations in life where that's kind of useful. And so by definition, we say that two functions f and g are inverses of each other if when we compose them in both directions, they undo each other. Okay, meaning that if I compose g with f, I get back the original input. And if I compose it the other way, f with g, we get back the original input. And so for example, just to take a basic example, if you have a function 3x plus 2, this is how I teach inverses when I'm doing this, like in a pre-calc class. We say, okay, what does this function do? It tells us to do two things: take x, multiply by 3, and then add 2. And so when we do the inverses, we do the opposite operations in the opposite order. So I could say, let's take some number x, multiply or subtract 2, and then divide it by 3. And then you could check that if I compose f with g of x, this would mean I'm going to compose this function. I'm going to take g, which is x minus 2 over 3, and plug it into f. and all of that gives us x. So that checks out. And then you, of course, need to check in the opposite direction. Okay, so we're just finding the function that does the exact opposite stuff. That's what we mean by inverse. And the way that we check that carefully is we check the composition in both directions. And when that relationship is satisfied, then we call that function g the inverse of f, and we denote it with a -1 up top. That means inverse, not reciprocal. On behalf of the math community, I apologize for that abuse of notation, but it's out of our control. So we just got to deal with it. So that means inverse function and not reciprocal. And so kind of the main result that I want to get at today is that, well, why is it nice that we want functions to be bijective? And the reason is if a function is bijective, then it has an inverse. And if a function has an inverse, then it's bijective. So we could kind of redefine invertible as bijective. They kind of mean the same exact thing. So if I ever want to prove is a function invertible, what I need to do is either create an inverse and prove that this satisfies the properties of being an inverse, or I can do a non-constructive proof and just show that the function is bijective and therefore it has an inverse, even if I don't know what that function is. Yeah, so if we kind of just want to go through the proof of how this goes, since this is an if and only if proof, we have two directions to prove. So we've got those labeled. So if we were to do the forward direction, that means we would want to show if something is invertible, then it's bijective. So we're going to start by supposing this function from a to b has an inverse. And then what we want to show is as a result of that assumption, we get that f is bijective. And so in order to show that it is bijective, we have surjective and injective properties to prove. So first, this sentence here proves the surjectiveness. Since we assumed f is invertible, then we know that this is true by the definition of inverse. And so now we just found, okay, here's a y value, which is some arbitrary thing in the codomain. I now figured out that I have an input, namely x is equal to g of y. Right, then basically what we're saying is, right, we pick any y in the codomain, I can find an x, which is mapped to that value y. And I'm going to define that x to be, it's what we get when we plug y into g. Questions? And then we would also want to prove the injective property. And here they're doing this using the contrapositive. So let's assume we've got elements x1 and x2, and their outputs are the same. Outputs of f are the same. Then what we can do is if we apply g to those outputs, since g is the inverse of f, that means when I take and plug this into g, they undo each other, and there we go, and we get x1. And when I plug this in over here, again, or we get that. And so if the outputs are equal, right, this implies that the inputs x1 and x2 had to be equal. And that gives us injectiveness. Let's see, my delay has not caught up to me yet. There we go. So just make sure you're keeping up, even if the details here, you need to think about it a little bit more. Just think about the bigger structure of the proof at least, right? We've got an if and only if. We have a forward and a reverse direction. In the forward direction, we need to prove bijective. So that's two things. We need to prove it's injective and surjective. So that's what we did in this step. Then in the reverse direction, we start with a function which is bijective, and then we want to show that it has an inverse, that it's invertible. So we construct a proof that satisfies that property. And so the fact that this function is surjective is going to give us a way of defining this function. So we define this function g, which maps in the opposite direction by saying we're going to take some element in the set B, and what is that going to map to? It's going to map to the element that is the pre-image of y. And because it's bijective, we know that every element has a pre-image, and that pre-image is unique. So that gives us a nice function. So here, big takeaway is that bijective and invertible are equivalent properties, essentially. Questions? Okay, so then when we're kind of going through these, I want to go through the kind of pre-calculus-y ones a little bit quicker so that we can think about some of the later ones before we go. But if we want to think about whether these are invertible or not, then we just need to think about whether the function is bijective, right? And so these are functions that we've essentially thought about already. If f is going from r to r, this is not invertible since it's not injective. And it's not surjective. So no point trying to find an inverse for that. When we go to B, same function, but now we've adjusted the domain to fix the injective part of it. So if we restrict our domain to only non-negative things, every input now goes to, each output has a unique input from it. So this is going to be injective. But we still haven't solved the problem of it being surjective, since this only maps to values that are bigger than or equal to 0. And if we similarly restrict the codomain, then we could get a bijective function out of this. So one thing to point out here is that this property really depends on, whether something is bijective really depends on what the domain and the range and codomain are, which depend on the function, but it's not just the function itself, but also the what is the domain and codomain that have a role here. Any questions about those? In H, we do have an inverse. Hopefully you recall natural log. So if I wanted to prove that this is invertible, I could either go through and prove that this is injective and surjective. So if I want to prove this, let me just consider a function. Maybe I shouldn't get ahead of myself and declare it the inverse. I'll call it g of x, which is equal to the natural log. And what we would want to show is that this satisfies the properties of being an inverse. Sorry, I forgot about my delay. So we would consider this function g, which is a natural log. Then we want to show when we compose it in one direction, first exponentiate, first do h, and then do g, they undo each other. And when we compose them in the other direction, we also get x. So now we've just proven that g of x is the inverse of h. Okay, so I think we've dealt with the sign quite a bit now to hopefully agree that it's not invertible, but when we restrict domain and ranges, we can get an arc sign. We can define some sort of inverse once we restrict things like we did with x squared above. But if we're talking about from all of R into all of R, it's not going to be invertible. And this function over here is invertible. So we could show that that is going to satisfy the properties of being an inverse function. Questions? Got one more minute left, so I just want to leave you with some kind of ideas to think about F, since you have a question like this on your last homework assignment, pretty similar, a map from Z cross Z into Z cross Z. We want to think, is this surjective and injective? And so it's almost like a multivariable calculus sort of map. We're going from Z2 into Z2. So it's a little bit more complicated, but we want to use the same definitions here. So let me just say, if you're trying to prove injectiveness, then kind of one standard way of doing it, again, is by the contrapositive, which would be showing, well, let's take two inputs and assume, right, that we have input A, B, and C, D that both give me the same output, and then try and show how does this imply that A should equal to C and B should equal to D, right? Now we've got two things to prove here. We need to show that the first coordinates are the same and the second coordinates are the same. So basically what you're trying to show is that AB is equal to CD. If you can prove that, then we've got injective. Otherwise, maybe think of a counter example. And if you want to show that something is surjective, that means you can take kind of any general output and you'd like to find, okay, what are the inputs A and B that would give me this certain output I'm calling PQ. And the thing you want to keep in mind here is that you're restricted to integers. So if you get things like, you know, the only way that I can map to a certain output is if my inputs are rational or, you know, like fractions and things like this. That means, you know, we can't take A and B equal to fractions and get PQ out. A and B have to be integers here, so just keep that in mind. Okay, we're out of time on this one, so if you do have any, it's not due tomorrow. This is the one that's due next week, has a function like this. So if you have some questions on it, you know, just let Lindsay or I know. Otherwise, yeah, good luck with your homework that is due this evening. And I will see you guys on Wednesday. So the last quiz is due on Wednesday. Please, you know, take some time to complete your FCQs again. I'll keep reminding you until we get that 80% mark. But thanks everybody, and I'll see you guys on Wednesday.